Good morning. We're getting through it. We're getting through it. All right. So I know I talked about the quiz last day, but I just wanted to remind you because there's some new material today that we're going to talk about that is on the quiz. So I just want to make sure that you practice that before you do the quiz. Okay, so quiz number 4. Opens Friday, so tomorrow. I think it's set to open at like 7 in the morning or something. And we'll close Sunday at midnight. Okay. Just like all the others, it's a 50-minute timed quiz, and it's based off of the assignments, of course. And I remember feeling as a student, this was nothing like the assignments, but I promise they are. If you come back to them, then you'll be convinced. But it's hard when you see things for the first time, right, in a quiz. So that's why it feels a little bit harder, but I've set the quizzes up so that they prepare you for the final exam, which is coming just around the bend. But we'll focus on quiz 4 for now. Okay, so same thing. It's a 50-minute timed quiz. And so you can use the lecture time on tomorrow to do it if you want to, but you don't have to, right? It's just that I made it the same amount of time so that you have it scheduled if you need that. Okay, and so here, one thing that I wanted to highlight is that all these assignments, assignment 11 is kind of a joke assignment, right? It's just a little itty bitty assignment, but that's to help you boost your grades, right? Assignment 12 makes you work a little bit harder. And then assignment 13 is on the 2 sample means. So that's either paired or independent samples. So you get a little bit of practice reading those and figuring out which type of question you have. And then assignment 14 is an assignment for the material that we're covering today. Okay, so make sure that you do assignment 14 before doing the quiz. So this is all, maybe I'll scoot this over just a bit. Quiz number 4. Okay, so here, assignment 14 covers the material that we're about to do today. Covers today's material. So be sure to practice it before attempting the quiz. Okay, so at least practice it. Notice, so I've set the due date. It's not due until next week, but that's just to kind of, if you wanted to kind of, oh, I get the idea, okay, but I want to focus on it later, that's fine, you can do that. But it is on the quiz, right? So just be prepared for that. So be sure to practice it before attempting the quiz. And that's where I wanted this little star here. Whee! Okay, so that's just a heads up. Next week is our last week, right? Oh my gosh. And I do want to just highlight here. So quiz number 4, of course, that means that there's no video. You can use the time for the quiz if you want. but you don't have to. Okay, so like I said, next week is our last week. That's crazy, right? And there's still a lot of material that we need to cover, but it's all fun material from here on out. So even though we could do hypothesis testing and confidence intervals with regression, which is what we're gonna do next week, we're not going to. Okay, so that I'll leave that for another course, a second course. And so we're just going to talk about regression, and I find that it's kind of the most fun chapter because all of a sudden things are feeling a lot easier. It's different, right? So just kind of be prepared for that. It's different from what we've been talking about, but it's also kind of, it's a fun chapter. Okay, so what I want you to do or try to do is read these sections for next week, right? Just to be prepared, because we don't have a lot of time to cover all that material, and so it would be really helpful if you've read it and you've seen it once before, and then when I talk about it, it's the second time that you're hearing it. So even if it doesn't make sense when you read it, right, that's okay. We'll talk about it and hopefully that'll make more sense. Okay, so read these sections and maybe I'll say to prepare for next week. Okay. I was going to rewrite all of that. What a mess. But anyways, that's okay. Clean up a week at least. There. Okay, so kind of a lot going on, of course, wrapping up. Same thing with the other quizzes, right? If you upload your work and you find that when you go back and look at your quiz and you find that, oh, I actually entered that wrong, or I had it right in my work, but then something happened, I was in a hurry. As long as you've uploaded your work within 10 minutes of submitting your quiz, then I can go and I can look and I can make adjustments, right? So you don't have to submit your work, but it's a good idea to submit your work, okay? All right, so 7.4 is on power calculations. Which we are skipping. I know, don't tell on me. No, everyone skips it. Which we're skipping, right? But you can read through it. It's not tested, so don't worry about that. But if you're interested in power calculations, then you can read that section. Right? It is a nice compact summary. And now, moving on to 7.5, right? We had the same progression that we did with proportions, right? We started with one sample proportion, and then we moved on and we said, well, what if I want to compare two proportions? And then we said, well, what if I have more than two proportions, right? What if I have 3 or 4 or 5 groups, right, that I want to compare? Then we use the chi-squared, right, instead of a z-test. And then so now we're going to have that same progression, right? We started with one sample mean, and then we said, okay, well, what if I have 2 samples? Sometimes they're paired, right? So then we treat them as a paired sample means question. Or if they're independent samples, then we treat them as independent sample means, right? And so 2 different types of questions there. And now we're saying, okay, well, what if I have more than 2 means, right? What if I have, and the example in the textbook talks about, okay, well, what if we have more than 2 sections of a class, right? For example, this class, I think right now there are 4 sections, right? So there's 4 sections being offered. And what if we wanted to talk about the average grade and compare the average grade between these four sections? Okay, And so we can do that, and that's what we're going to talk about today. Okay, so kind of the progression ends here. And so now we've talked about how do we handle up to many proportions, and today we'll talk about how do we cover or talk about up to many means. Okay, so 7.5 is comparing many means with Anova. Comparing many means with Anova. So many means is going to be more than 2, right? And so more than 2, right? Because if you have 2 samples, right, so 2 means, then you should use a t-test, right? A 2-sample t-test, and whether they're paired or not, right, that's going to determine what t-test to run, right? But for more than 2 means, we use what we call ANOVAs. Now, ANOVA stands for Analysis of Variance. Okay. And yes, just like the chi-squared test statistic could be applied to a goodness of fit test, a test for independence. We didn't do a test for homogeneity, but we could have, right? So the same test statistic can be applied to many different scenarios. Same with the ANOVA. So we're going to talk about the ANOVA in terms of means, but we could also talk about them in terms of coefficients in a regression, for example. And there are others, but those are the main ones. Okay, so just like all the other test statistics, they can be applied to different scenarios. Okay, so we're going to focus on one, which is the means. Okay, so if we have more than 2 means that we want to compare, right? So let's just lay out the scenario, right? What type of problem am I going to have here, right? And so if we want to compare, and just for simplicity's sake, let's just talk about 3 groups, right? That's more than 2, but it's kind of the smallest version of what we're going to do. We could consider, 3, 4, 5 groups, 10 groups if we wanted to, although it gets a little bit boggy, right? And so if we want to compare the means of 3 groups, right, which is more than 2, right? Then what would I have to do? I would have, let's say I have groups A, B, and C. Okay, so if I have groups, my groups are A, B, and C. And let's say I have some mean measurement for each of these, right? So the average grade for group A, the average grade for group B, and the average grade for group C, for example. Or maybe we're talking prices or heights or weights or distances or anything numerical, right? But we have them split across groups, okay? So then if I wanted to do this comparison, using the tools that we have, we could do something like, okay, I'm going to look at how does A compare to B? Okay, 2-sample t-test. How does A compare to C? Another 2-sample t-test. How does B compare to C? Right, and that's another 2-sample t-test. Okay, that we could do that. I'm going to tell you why we shouldn't do that. Okay, we could consider the pairwise comparisons. Right, and so maybe I'm going to put this down one because it's page break. So what if I wanted to compare A and B, A and C, and B and C. Right? Comparing A to B is the same as comparing B to A, so I don't need to consider any other combinations, right? I have all these combinations, and so, right, I looked at A to B, A to C, B to C, and then I've covered all these different options, okay? But what happens is that every time that I do this, I open myself up to a type 1 error. What's a type 1 error? That's the alpha level, right? So the type 1 error is the probability of rejecting H naught when it shouldn't be rejected, right? So it's if I make a mistake, right? So every time that I do this, I open myself up to a type 1 error, right? We don't want to do this because we open ourselves up. Oops. Open ourselves up to a type 1 error with each comparison. Okay, and I'll even put an exclamation mark there. Okay, so that's not something that we want to do. Okay, so what we want to do is, all right, wouldn't it be so nice if we had a test that would tell us, hey, if I go in and I look at these comparisons, these pairwise comparisons, am I going to find something? Right, so imagine instead of having just 3 groups, imagine if you had 10 groups, right? The means of 10 groups that you wanted to consider. Now try figuring out how many combinations you have, right? All of a sudden it's too many, right? And every time that we do it, we open ourselves up to a type 1 error, right? Which is 0.05 at each test. That's bad, right? And so the Anova lets us look in, and I kind of imagine it being this like box. So it lets us look in and ask, hey, is anyone different in there? Right? It doesn't tell us which one is different, but it tells us if one is different. And if we find out that one is different, then we can go and we can find it. Okay. So instead of doing pairwise comparisons, we can run an Anova, right? We can run an Anova. And when I say run an Anova, what I mean is I can do a hypothesis test where the test statistic is an Anova. Okay, and so here I just want to clarify, we can run an Anova, which really means do a test or do a hypothesis test where the Anova is the test. Where the Anova is the test. Okay, so so here, just to finish the sentence, so instead of doing pairwise comparisons, we can run an Anova. That's what we say. We can run a t-test. We can run a z-test, right? And so that's kind of the common terminology that we use. And so we can run an Anova, and I probably haven't used that terminology before because I don't think that you were ready for it. But now that we've seen all these, I think it's going to start to click a little bit more. So now we can run an Anova, which means do a hypothesis test. Okay, and so we can run an Anova to see if there is any group that's different from the others. To test whether any of the groups, and maybe I'll continue here, any of the groups are significantly different from the others, are significantly different from the others. Okay. It won't tell us which one or ones potentially are different, just if there is something going on. Okay. It will not tell us which groups, potentially plural, right? It's just going to say, hey, there's something going on in here. You should look at this, right? So it doesn't tell us which one. It just, is there something going on? Okay, so it will not tell us which groups potentially are different. Only, maybe I'll end there. I'll end that sentence there. Okay. So if we find a significant ANOVA, then we can consider and we can find those differences, but we have to make some changes to our testing before we do it. Okay, so what are some of the things I've said you need to know in order to tackle any hypothesis test at this point, right? So an ANOVA, which is what we're talking about today, is a hypothesis test. So one of the first things we should talk about is what are the conditions for running an ANOVA? And I am kind of speeding through because there's a lot of theory behind an analysis of variance, but given our kind of time restraints here, I just want to get down to how it works for us, the things that we need to know, okay? But maybe I should give you just a quick example of how it works. So the idea, why is it called an analysis of variance when in fact, what we're analyzing is the means, right? For me, that was kind of a tricky thing to wrap my head around, because I always thought, oh, well, I'm actually comparing the means of a couple of groups here, or many groups. So why is it called an analysis of variance? And the reason is, let's see here. See if I can find, okay. If I have something like this, right? If I have lecture group A, B, and C, right? So I have 3 different lectures, right? Very similar to what we have going on. And then we have the grades, right? So each lecture group is going to have some distribution of grades, okay? And remember, these are the medians, but if the box plot is symmetric, whoa, going way back to the beginning, right? If the box plot is roughly symmetric, then the mean is around the median, okay? And so, so what we have are these bars, which basically represent the median, or sorry, the mean. Right, so this bar is the median, but recall that if the box plot is roughly symmetric, the median equals the mean, right? So what we're comparing here are these lines, right? Those are the average grades in each lecture section. So we've got these groups, right? 3 groups. And we're comparing the means across the 3 groups. We want to compare the means across the 3 groups. if I asked you to look at this, right, and I asked you, hey, is there a difference in the means, do you think? Right? What are some of the things that so pay attention to the things that your brain looks at, right? It looks at the spread, right? It looks at the spread, the overlap in spread across these groups, right? That's one of the things that your brain looks at. What is the spread? That's the variance or the standard deviation. Remember, the standard deviation is the square root of the variance, right? And so the variance is the spread, right? And so what we're actually analyzing and our brains analyze are the spreads, right? The spreads relative to what? Relative to the overall spread, right? So the analysis of variance comes from, okay, if I have this amount of spread in all the groups and overall I'm spread out over roughly the same amount of space, then what do our brains tell us? Well, it tells us that no, there's not really a significant difference here, right? So there's another kind of, I should draw on this so that it comes up. There's another graph just to show it. Oh, where is it? Here. Okay. So here's another example, a similar example, right? And so here, these are groups, I think 1, 2, and 3. If I asked you, okay, do you think that there's a significant difference between any of the groups between 1, 2, and 3? You would probably say no. Why? Because the spread is, these things are all so spread out and they're covering roughly the same amount of space. And so for that reason, you would say, no, not really, right? But then when you look at groups 4, 5, and 6 here, right, because the spread is smaller and then it is kind of distinctly moving across the groups here, then you would probably start to think, okay, there might be something going on here, right? Group 5 might be significantly higher than the other two. Okay. What I did there is actually a bad thing, right? I don't want to have some preconceived idea of what's going on here. That's what we call data snooping. It's hard to avoid, right? Because we see the data and we say, oh, I know what's going on here, right? And then we test that, but you should be testing all of them using an Anova first, okay? So that's kind of the idea behind an Anova, and of course the textbook goes through and it talks a lot more about it around it, right? So if it doesn't really make sense, it's okay, right? Maybe fill in the gaps reading the textbook instead. But for us, we need to know how to apply it, right? So how can we read the output? How do we get the output? How do we do this hypothesis test? Okay, and so let's talk about the conditions for an Anova. I think what you'll find is the assignment I posted doesn't talk about the conditions, so you're safe to just assume that they've been satisfied. But in real life, of course, we need to know what the conditions are. But the reason I kind of glossed over it is because they're pretty basic. Okay, so we start with independence again, right? Independence in this case means that the observations are independent within each group, but also across the groups, which if we've randomly selected our data, that's the safest way to ensure that that happens. Okay. If the data has been randomly selected, we can assume that the data or the observations within the groups as well as across the groups, right? So notice how we have this terminology of within the groups, but also across the groups. Okay. So here, let's highlight that. So within the group, but also across the groups. So that distinction is going to be important. Okay, so if the data has been randomly selected, we can assume the observations are independent within and across the groups. Right. So that's your independence condition. Same thing as always, right? Was the data randomly selected? Yes. So then we can assume independence. That's good. Okay. And maybe what I'll say is normality here, because that's usually what this condition is called. So what we have to check is that within each group, right, the distribution of each group or within each group is approximately normal. That's one of the conditions. So here what we said is, okay, the reason I can assume that the median is roughly the mean is because they're roughly symmetric, which means that they're normal, approximately normal. So one of the conditions is that, okay, these groups have to be approximately normally distributed. The distribution within each group is approximately normal. Right? Look for roughly symmetric box plots. We usually end up using side-by-side box plots here just because they're the easiest to kind of look for symmetry. Notice with those dot plots, it's really hard to tell what the overlap is in the data, right? So when we look at these box plots, it's hard to tell if it's symmetric or not, right? And so that's why we use the box plots instead, side-by-side box plots. And finally, the last thing we have to assume is that we have constant variance or approximately constant variance across the groups, which means they have roughly the same spread. So it's a constant variance assumption. The groups must have roughly the same spread. Roughly the same spread. Right, and so what we can do is we can compare the standard deviations, right? And if they're approximately the same, then we're good. Compare the standard deviations. To make sure they are roughly the same, right? They don't have to be the same, but roughly the same. Okay, good. So those are the conditions that we have to check. And like I said, we're kind of glossing over that. I have to say it because it's important, but it's not something you have to worry too much about, especially being open book. You can just flip to it and have it there. So what are we testing here? When we run in Anova, right, we're doing a hypothesis test. So what does that mean? What is my hypothesis? Okay, so step one is to state my hypotheses. Sometimes for ANOVAs, it's stated in words, I actually prefer that you use notation still. Okay, and so, but the alternative hypothesis ends up being in words because the mathematical notation is not nice, right? And so here, right now we're at this point where I give you the null hypothesis and how you run the test, and then you'll be able to do this test, right? If I give you output, you can set up your null and alternative hypotheses, and you can find your p-value, right, from that output. And so we're not doing the calculations really anymore. It's going to be a table, so you'll see it's a little bit different, but we'll talk about it. So the null hypothesis for an Anova is mu1 is equal to mu2. Okay, that looks similar, right? That's from the two independent sample means that we talked about last day. But remember, now we have more than two groups. So we keep going, is equal to mu3, and we let it run all the way up to is equal to mu k. Usually we use k. I was going to use I, but let's use k, right? And so we're leaving room for k groups. Yeah. This is basically saying, or this is saying, all the means are basically the same, right? There's not a single one that's significantly different from the others here. Okay, so the alternative hypothesis would be slightly different from what we're used to, right? It's going to be in words. It's at least one of these mu i's. Okay, so the alternative hypothesis is in words, at least one mu I is not equal to mu j. What does that mean? I use I and j because I'm talking about two different groups, right? And so mu2 is not equal to mu3, for example, or mu3 is not equal to mu1. Okay, so at least one of those is different from the others. So at least one, and I'll put this in brackets because that's the shorthand version, mu I is not equal to mu j, but that's confusing in the beginning, right? So at least one mean is significantly different, from another mean. If we take a step back and we say, okay, if I have mu1, mu2, mu3, and mu4, for example, right? The reason I say at least one, so let's say mu3 is significantly different from mu2, right? So it's at least one mean is significantly different from another mean, right? At least one other mean. And maybe that's what I'll clarify here. From at least one other mean. Because just because 3 is different from 2, for example, that doesn't mean 3 is different from 1, right? It doesn't have to be. Okay, so that's why we have this very vague statement of, okay, at least one mean is significantly different from at least one other mean, right? And so here, that's what this is saying, right? Mu I does not equal mu j is saying, is summarizing this, right? So you could say at least one mu I is not equal to mu j, and that is your alternative hypothesis. And maybe what I'll do is I'll copy this, and just delete this and have the two options side by side. How about that? At least one mean is significantly different. Just reorganizing here, right? Or or at least one mu I is not equal to mu j. That's the same thing that we're saying. Okay. Step 2 is in this case going to be combined with step 3, find the p-value, because it's going to be given in the output. So I will break it up here, but step 2 is do the test. For an Anova, that means do an F test. So the Anova is the name of the hypothesis test that we're doing, but this is really calculate an F statistic. So this is like the first time that the name of the test has a different name from the actual test statistic. That's okay. So calculate an F statistic for the Anova. Okay. You'll be given output, okay? But given some output with empty spaces, you're expected to be able to fill in these spaces. So I want to talk about the relationships within the table. Okay? So you will be given the output for the Anova. And we'll need to know the relationships within the tables. We'll need to know the relationships within the table. Right? So usually how we do that, how we test that is I give you a table and some of them have empty spaces, but you have just enough information to fill in those empty spaces. And then of course you have the entire table. Okay. So a general Anova table is going to look like this. Okay. It's going to have the header row. It's going to have at least, let's do three rows below it. Okay. And so what we have here is, and maybe I need just a smidge more space here. Okay. So remember, the analysis of variance looks at the variance, so the spread within the groups and then across the groups. Okay. And so what we do is we have what we call the groups. Now, it depends on the output, right? And so some textbooks are going to call it, I think it's the between and then the within, but we're going to talk about the groups and the errors. And let me just confirm that actually, because I was looking at, I was thinking about some specific output here. Just a second. Okay. So this is what the output is going to look like. But before we bring this in, and I will bring this in, I want to just talk about the relationships within the table. Okay, so we're not quite there yet, but that's what we're looking at. So maybe to match the textbook, I'll call it residuals. I think it said residuals. And then we're going to have the total. Sometimes we don't get the total, but we can find the total. Okay. So the first row here is going to be the degrees of freedom. Okay. And the residuals, I'm going to write errors, or the error maybe above the residuals, because usually we use E for the error. Okay. So the degrees of freedom for the groups is k minus 1. That brings us back to the chi-squared, right? For the chi-squared goodness of fit test, we're comparing multiple groups. So the number of groups minus 1. Same deal here, right? So across the groups, we have k minus 1 degrees of freedom. For within the groups, so DFE, I want to call it, is n minus k degrees of freedom. When I talk about the total, our minds probably automatically go to addition, and that's correct, right? And so the total degrees of freedom is going to be n minus 1, because k minus 1 plus n minus k, right? K minus k goes away, and then you're left with n minus 1, right? And so your total degrees of freedom is n minus 1. So far, that's sort of familiar, right? We're kind of putting things together here. Okay, so then the tricky part, and of course, if we had more time, we would talk about how we find these sums of squares. Okay, so this is sums of squares or sum of squares. And for us, right, lack of time here, I'm just going to give you the sums of squares for the groups and the sums of squares, oops, for the error. And then, of course, the total is the two added together. Okay, and the degrees of freedom, same thing. DF total is k minus 1 plus n minus k, right? If I break out these brackets, k minus 1 plus n minus k minus k goes away, and then n minus 1. Excuse me. Okay. So these are some of the relationships to keep in mind, right? If you have the total degrees of freedom and you have the group degrees of freedom, you can find the residual degrees of freedom, right? Or the error degrees of freedom, because they have to add to the total, right? Same thing with the sums of squares. Even though we don't talk about what they are, right? We know that there's this relationship that this plus this has to add to this. So if one of these are missing, then that's fine. You can just go ahead and find the missing one. Okay. So then we're going to talk about the mean squareds. Mean squares. And we're going to have the mean squareds for the group, which is actually going to be the sums of squares for the group divided by the degrees of freedom for the group. So notice how it's the previous two rows, one divided by the other. So that's kind of fun. Divided by the degrees of freedom for the group. And same thing with the mean squared of the errors. It's the sums of squared of the errors divided by the degrees of freedom of the errors. Okay. So we don't talk about the total anymore. That's fine. We don't need it. Okay. Because then our test statistic is F, right? And so this is our F is our test statistic. And so our F is going to be the previous MS divided by, so the MSG divided by the MSE. So F is the MSG divided by MSE. And notice how there's nothing here. Okay, so there's nothing there. And we actually stopped talking about the totals at this point. Okay. So then, like any test statistic, we have to find a p-value, and that is our last thing. in the table, it'll be given here. So we can use an F table. The F table needs to know both of these degrees of freedom, and it's just too much work to be doing by hand. And so it's just going to be given in the output. Okay, and so here, this will give you the p-value. And same thing as all the other p-values. If the p-value is low, then you have enough evidence to reject the null hypothesis in favor of the alternative, which tells us that if we go back to our hypotheses, right, it tells us that there's at least one mean in here that's different from at least one other mean, right? And so same idea as before, right? So step 3, find the p-value. Okay. The p-value will be given in the output, right? Specifically here. Okay. So then, right, our conclusion stays the same as before, right? So step 4 is our conclusion, right? And at this point, I think we're pretty comfortable saying, okay, it's the same as before, right? If the p-value is less than the alpha level, so if the p-value is less than the alpha level, we have enough evidence to reject H naught. H naught in favor of HA, which means, right, there's at least one mean, right, among this group of means, right, or among these groups, there's at least one mean that's significantly different from at least one other mean. Which means there is at least one mean that is significantly different from at least one other mean. From at least one other mean. Okay. So then what we do is, and I just want to make sure that I didn't skip anything that I wanted to say. Okay, no, we're good. So then if we find a significant ANOVA, right, which is what we're going to start calling this, right? So if I have enough evidence to reject H naught, that means I have a significant test, right? So if I find that I have a significant test, a significant ANOVA, then I can go in and I can consider the pairwise comparisons. Okay. So here I want to say, okay, so if we find a significant ANOVA, right, which means that the p-value is less than the alpha level, that's what it means to be significant, right? So if we find that, then we can go through and we can consider the pairwise comparisons. Then we can consider the pairwise comparisons. To determine which means are different from each other. To determine which means are different from each other. are significantly different from each other. Okay, but there's an adjustment. Okay, so there are many different things that we could do, but the most basic solution that we have is we make what we call a Bonferroni adjustment. Okay, and so I feel like it's the, sorry, I'm just blanking on what I divide it by. Let me just find it here. Okay. Because I blanked on it, I may as well steal it and bring it in here. Okay. So, so we can consider the pairwise comparisons, right? But what we do is we have to make an adjustment. Okay, so however, we need to use a different alpha level, right? The alpha level is the probability of making a type 1 error. Remember, that's where we started. We said, okay, every time that I do these pairwise comparisons, then I'm opening myself up to type 1 errors every time. 5% chance, 5% chance, 5% chance, right? And those things add up. So that's not good. We don't want to do that, right? And so we need to use a different alpha level, right? So that we make an adjustment to the probability of making a type 1 error. So the alpha level, which is the probability of making a type 1 error, right? So we need to use a different alpha level. And the most common slash, I want to say simplest correction that we can make, slash simplest adjustment is called the Bonferroni adjustment, which is fun to say too. Bonferroni adjustment. So instead of just using a default of 0.05, right, that's typically what we're using. Okay, so when we've got these multiple pairwise comparisons, what we need to do is we basically divide up our alpha across the number of comparisons that I'm making, right? For 3 groups, I had 3 different comparisons, A to B, A to C, and B to C, 3 different comparisons, okay? How do we determine how many comparisons I'm making, right? And so here, so K, capital K is the number of comparisons. Okay, so that it's here, but I just wanted to highlight it. So if there are lowercase k groups, then usually all possible pairs are compared by k, which is k times k minus 1 divided by 2. For example, right, we saw A, B, and C as my groups. Then I did A to B, I did A to C, and I did B to C. Right, so here, this tells me that lowercase k is 3. Right, so then what do I find? I find that capital K is 3 times 3 minus 1 divided by 2. 3 times 2 is 6 divided by 2 is 3, right? And so that's why it's 3. 3 comparisons. So another thing we could talk about is, okay, well, if I have 10 groups, how many possible comparisons could I make? Okay, So for example, if we want to compare 10 groups, right? How many possible pairwise comparisons are there? How many possible pairwise comparisons could we make? So now K is 3, or sorry, K is 10. I was reading the notes. So K is 10 times 10 minus 1 divided by 2, right? 10 times 9, it's usually 90. 10 times 9 divided by 2, so I have 45 possible comparisons. 45 pairwise comparisons. It's good to know how to find the number of pairwise comparisons, just so that you could, if you had to, you don't have to, but if you had to list them all out, right, then at least you know how many you want or need, right? And so in this case, alpha 0.05 would have to be split into 45 pieces, right? So in this case, the Bonferroni adjustment, alpha star, we denote it by, is the alpha, the original alpha divided by K. So what we do is we say, okay, instead of 0.05, I'm going to split this among the number of comparisons that I'm doing, right? So they each get a portion and then they add up to the total alpha that I want. Okay, so in this case, so for K equal to 10, which really is shorthand for 10 groups, right? We would use alpha star equal to alpha over K. Alpha star is 0.05, right? The alpha level is 0.05 by default, okay? Divided by 45, so then alpha star is 0.05 divided by 45, which is 0.00, I want to say 12111. Let me just confirm here, because it showed up as scientific notation and it's to the -3. So 1, 2, 3. Okay. And it keeps going. It's one repeating, but that's fine. I'll end it there. Okay. What does this mean? That means that my p-value has to be less than this to be considered a significant pairwise comparison. Okay, and maybe here. This means the p-value for a pairwise comparison must be less than 0.001. That's really small, right? So it has to be extremely small, which we translate to extremely significant, right? So extremely significantly different to be considered significantly different. Okay, so this means the p-value for a pairwise comparison must be less than 0.0011 in order to be considered significant. Considered significant, right? What does this mean in terms of rejecting H0? Really what this means is this makes it harder to reject H0. And remember, the type 1 error is rejecting H0 when we shouldn't have, right? So if we make it harder, then we're decreasing that type 1 error rate, right? And so here, what we're actually saying is we have made it harder to reject H naught, right? So that's really what we're doing. One of the things that can happen here is that even if we find a significant ANOVA, once we look at the pairwise comparisons, because we've adjusted the alpha level, it's possible that we don't find a significant difference, and that's okay. It just means that we don't have enough data to support what we're trying to say. So the ANOVA might say, yes, there is something going on here, right? But maybe we don't have enough data for the pairwise comparisons to get that p-value less than the adjusted alpha level. Okay, so one thing it is possible to find a significant ANOVA, which really is saying, okay, there is something going on here, but then when we look and we consider the pairwise comparisons, we don't find a significance, right? Because we have to use these adjusted alpha levels. So it is possible to find a significant ANOVA but it is possible to find a significant ANOVA where no significant pairwise comparisons can be found because of the adjusted alpha level. Where no significant pairwise comparisons can be found because of the adjusted alpha level, right? Usually it's because our sample sizes are too small. Okay, so usually this is due to small sample sizes. It's really hard to get a small p-value if you have a small sample size, because it depends on the sample size. Okay, so right, and if we think about how those relate, right, small sample sizes, we have our data, but we also know if I collected another small sample size, it might be quite a bit different, right? So there's a lot of variability there. Whereas if I have a large sample size, then I can consider my results fairly robust. And so my conclusions are stronger, right? And so then I get smaller p-values, right? That's kind of above and beyond where I expect you to be, but there's a link throughout here, right? Okay, so let's have a look here. I haven't talked about the pooled standard deviation, but usually it's part of the output, like it is here. Let me zoom in here. Okay, so if you're doing the pairwise comparisons, then you're going to use this pooled proportion, which is part of the output. I guess I should say that. Just as a quick note here, you're not going to be doing any pairwise comparisons, so that's why I'm kind of glossing over it, but let's just cover all our bases. So note, if you are doing the pairwise comparisons, you should use the pooled proportion, or sorry, the pooled standard deviation in your calculations, and the pooled standard deviation, so the S pooled will be given as part of the output, will be given as part of the output. So we don't talk about how we found it. Okay. So for example, here's some output that we can look at. So, and here I just want to highlight this S pooled. It's that one. Okay. It also gives you the degrees of freedom for the t-test, but we're not going to do it. So I'm going to ignore this bottom part. Right? But let's talk about what was the, I'll bring in the original. I want to go here. Okay. So with our last couple of minutes here, let's go through this question. College departments commonly run multiple lectures of the same introductory course each semester because of high demand. That happens for us too. Consider a statistics department that runs 3 lectures of an introductory statistics course. We might like to determine whether there are statistically significant differences in first exam scores in these 3 classes, A, B, and C, we'll call them. Describe appropriate hypotheses to determine whether there are any differences between the 3 classes. And I'm going to follow this up with, because we don't really have time, assume the conditions are satisfied. Cheating. Yeah. So what's my first step then, right? Step 1 is to state the hypotheses, which in this case, my null hypothesis, remember, is that mu1 equals mu2 equals mu3 equals mu4 all the way up to however many groups. Now let's be specific and use A, B, C instead. Makes it look a little bit nicer. So mu A is equal to mu B, which is equal to mu C. Only got 3 groups. Okay. So then my alternative hypothesis is that at least one of the means is significantly different from at least one of the other means. At least one of the means is significantly different from at least one of the other means. One of the other means. Good. So now I can bring in this output. So step 2 is to do the test. But you'll be given output that you can just use. So copy. And click this up here. The lecture is the groups, right? A, B, C. That's the lecture section. So we have 3 groups minus 1 degrees of freedom. So that's 2. And we have a sample size of how many? Well, I know my total degrees of freedom, which isn't shown here, is n minus 1. So I have 2 plus 161, that's 163. And then, so it adds to 163, which makes 164, right? So those are the calculations that I'm expecting you to be able to do, right? So just knowing the anatomy of that table, like we talked about, okay? But let's go. So the sums of squares will be given to you, right? But you know that the total has to add to these two, right? And then the mean squares is the sums of squares divided by 2. Let's just check it for the first one, right? 1290.11 divided by 2 puts me at 645.055. There's some rounding here, but that's okay, right? And so same thing for the mean squareds, right? It's going to be 29,810.13 divided by 161 is going to be 185.16. To find the F statistic, right, or the F value, I guess, that's going to be the 645.06 divided by 185.16, right? 645.06 divided by 185.16 is 3.48379779. Probably continues, right? But 3.48. And then here we have the probability of being greater than F. We're going to just, this is the p-value. And so step 3 is find the p-value. And that's this here. The p-value for the F statistic is 0.0330. We don't use that adjustment here, right? That's for our pairwise comparisons. We're just looking at the overall ANOVA. So let's use a default alpha level of 0.05, and then we can wrap up our conclusion, step 4. And just to give myself just a smidge more room, I'm going to bump this up here. Oops. Oh, I see what happened. There. Step 4 is my conclusion. Since the p-value of 0.0330 is less than alpha, I have enough evidence to reject H0, which means what? It means if I have enough evidence to reject this, it means that at least one of the means, so one of the exam means for a group is significantly different from at least one of the other means. So since the p-value of 0.0330 is less than the assumed alpha level of 0.05, we have enough evidence to reject H0 in favor of HA, and I know I'm out of time. I'm just going to wrap this up, but if you have to go, I totally understand. But I'll just finish the conclusion in our notes so that when I post them, they're there. So we have enough evidence to reject H0 in favor of HA, which means at least one of the lecture groups has a mean that is significantly different from at least one other group. Might be both, might be just one, we don't know, right? Which means at least one of the lecture groups has a mean that is significantly different from at least one of the other groups. There, we did it. Okay, so a little bit different, but we're so used to doing hypothesis testing now that it's just, and we don't do confidence intervals for ANOVA, it's just hypothesis testing. Same as chi-squareds, right? We stopped doing confidence intervals, we just did hypothesis testing. All right, so nice work. Make sure you practice, so do this assignment before you go into the quiz, and then you'll be all good to go. If you have any questions, let me know. Otherwise, good luck on your quiz, and I'll see you next week. And I'll stop this recording here.